evening, everyone. It is my pleasure. ఏంరా ఒక నిమిషం ఉండు. నేను చెప్పినప్పుడు వద్దు ఉండు. నేను చెప్పినప్పుడు వద్దు ఉండు. చెప్పు ఏమైంది? అది రాత్రి రాత్రి నువ్వు మాట్లాడుతున్నావు అక్కడ మీటింగ్ జరుగుతుంది. మరి దేవు వస్తాడు వస్తాడు వచ్చేకుండా నేనే వస్తాను. 5 minutes ఉండు. వాడు వచ్చి మాట్లాడు 5 minutes తర్వాత చెప్పేది నేను. జస్ట్ 5 minutes జస్ట్ 5 minutes ఆగిరా. 5 minutes లేదా కూర్చోరా. 5 minutes 5 minutes కూర్చో. నేను ప్లేస్ మైక్ ఆఫ్ చేసుకొస్తాను కూర్చో. 5 minutes చెప్పాను కదా పో. 5 minutes ఆగిరా. 5 minutes ఆగు. జస్ట్ 5 minutes వస్తాను. దూరంగా ఉండు. హలో సార్. ఓకే సార్, ఏం లేదు, జస్ట్ 28 ఉన్నారు సార్. 30 రీచ్ అవ్వగానే ఇంకో 2 members కోసం వెయిట్ చేస్తున్నాను సార్. వన్స్ ఒకసారి చేస్తాను సార్, చేస్తాను నేను. ఓకే సార్.
Sir Kamal sir.
Hi Purna. Yeah, I am here.
Sir,
may
I audible sir?
Yes. What about my voice? Is that audible?
Sir, yes sir.
Okay.
Sir, shall we start sir?
Yeah. Okay Purna.
Good evening everyone. It is my pleasure to introduce our esteemed resource person, Dr. K. Kamalapati, who holds impressive academic qualifications and professional experience in the field of power electronics and engineering. He completed his PhD in design and development of wireless power transfer with solar integration for electric vehicle charging applications from NIT Tiruchirappalli. In terms of professional experience, Dr. Kamalapati is currently working as a senior power electronics engineer at Capgemini Engineering, Bangalore. Prior to this, he worked as an engineer software development at MBTEL Technologies, Bangalore. We are fortunate to have him here today and look forward to gaining valuable insights from his expertise. Please join me in welcoming Dr. K. Kamalapati. Sir, please continue, sir.
Yeah, thank you, Purachandra Reddy, sir. Thank you all. Thank you to the management of SVCET and all the faculty and HOD of Tripoli, who is organizing this ATAL 2024 these sessions. All organizers and students, thank you. Okay, my screen is visible to all.
Yes, sir.
Yeah, my voice, everything is okay.
Sir, everything fine, sir.
Yeah, thank you. Uh, Good evening, all of you, faculty members, students, and all the participants from various colleges and institutes. Myself, Dr. K. Kamalapati. I'm working as a senior professional one as a power electronics engineer from Capgemini Engineering, Bangalore. Today, I am giving some brief knowledge what I did in my research and what I learned in my experience uh, through this session. The title of this session is Wireless Power Transfer System Integrated with Solar Power for Electric Vehicle Charging. Now, here itself, the title is very clear, wireless power transfer. I have to introduce the first topics, and after that, and how it is integrated to the solar power for charging of the battery through the power converters. First, the things contents to be discussed in this session is first I will discuss the two coil system and what about three coil system and what are the advantages and disadvantages over the two coil and three coil systems. And the second topic to be discovered, dual converter based wireless charger integrated to the solar systems, and see what is the advantages and which type of converter and how the modes of operations is going to be done in the dual converter based wireless power charger integrated to solar system. Now, first thing, what is the charging system? Different charging systems available in the day to day we are seeing nowadays. First thing, it is the onboard charger and off-board chargers. Now, off-board chargers and onboard chargers, you see here, it is connected to AC grid, and there will be onboard charger means within the body of the vehicle, it is integrated, and after that integration, it is connected to the battery, and there will be a converters, and it is connected to DC-DC and DC-AC converter will be there, and it is connected to the motor, and it is axle wheels, everything is interconnected. Now this is the flow of onboard charger energy. Now the other one is the off-board charger. Off-board charger, the converter, this part is going to be out of the vehicle, out of the vehicle. Now this type of vehicles is having a very bulky power electronic devices because the rating of these devices is more output chargers. This is a DC-DC or a full AC converter, and this is not possible to carry in the vehicle because the rating of the charging system is more. That's why the system is going to be connected outside of the vehicle. Now you see here, now this type of boxes will be there, electric vehicle charging station. Now this is the off-board charger, it is not the on-board charger. Now some vehicles is having the power converter, everything inside the vehicle also. Now, the charging is going to be happen manually, not wireless. So this is the scenario, whatever you see in nowadays in India, off-board chargers and on-board chargers. Now come to the next topic. This was in the other countries. It is going to be a lot of research is going to be happening. This one is the wireless power charger. Now here The main content is the power converters and the two coils is there. Now, the two coils is one is the uh, primary coil and this one is the secondary coil. You call it as a transmitter coil. This one it is a transmitter coil, and the second one is the receiver coil. Now, this the principle is the same. The transformer induction principle. Magnetic is going to be the flux is going to be links to the two coils, and energy is going to be delivered through the AC/DC converter and pickup converter, and after that it is going to given to the battery pack. Okay. Now there is a single line diagram. It is the practical system. It is going to be like this. Now you see the energy flow from a single phase or three phase system, and you can give it to isolation transformer or rectifier and high frequency converter. Now this is a very important. I'm going to wireless power converter. Now high frequency converter means we have to go for the inverter operations is going to be happens here, and we have to convert 50 hertz to the high frequency, which is a pulsating. Okay, and we have to go for 100 kilohertz or 85 kilo. Now the standard frequency is going to be 85 kilohertz for wireless power charging frequency as per the safety standards defined by the IEEE standards. Now 85 kilohertz we have to make it through the controlling, and it is given to the primary coil, and through this magnetic flux is going to be used in the secondary, and after that again you have to use the AC to conversion to DC, and pickup converter you can do it like this converter or not converter as per the requirement of the battery. You can pickup converter is going to take care, and it is going to charge the battery. Now, this is the structure of different charging systems available nowadays. Now, particularly, I am working on the onboard chargers with the company, but my research and all it is going to be the wireless charging. Now I will discuss the wireless charging systems. Okay, now first topic as I defined at first slides, development and analysis of the three-coil wireless charging system for electric vehicles. Now see, this is the just objectives, what explanation is going to be like this. Now see here, the objective is there will be a two coils. I already told three coil system or two coil system. There will be a two coils will be there. One is the receiver coil and one is the transmitter coil will be there. Now here you are using one more coil, that is the intermediate coil in between the transmitter and receiver coil. Now why you are using this intermediate coil? All things we can go through one by one. Okay, now where you are using the wireless power transfer system, it is a primary use nowadays in the charging of mobiles and biomedical applications, and also it is used in the electric vehicle charging. But the frequency levels is going to be different for different applications, not the same thing. But the thing is here, while going to the high frequency, the devices is going to be the very less things, and because the flux density is using the frequency, and devices is also going to be the less components. That is one of the point. But electric vehicles, they are defining to one frequency, and biomedical applications is going to be the other things, and some mobile charging, everything, electric tools, it is going to be the different. Now, here the main advantage is you are not going to manually uh, uh, charge the vehicle. Now it is just you are going to park the vehicle, and with exhaust there is a placement between the transmitter, which is at the ground coil, and the receiver coil, which is at the bottom of the vehicle, which is kept at the bottom of the vehicle. And once you have to kept and on the grid, and after some time the battery is going to be charge. Now you see this type of charging systems in all other countries like US, France, like that. While going to office, they will just go to a charging point and charge the vehicle and go to the office, and at evening time it automatically fully charged. Now this type of things is not nowadays it is a practical things in the India. Now in other countries we can see this type of applications. And also there is a several innovations will be there. Now there is a dynamic charging also is coming, and dynamic charging means there will in a road itself the number of coils is going to be placed, and the through the running the the vehicle battery is charged. That type of innovations is also research and development is going to be all research centers for the electric charging applications. Now see this type of structure. Now this is a complete structure where you are going to work. Now this is the terminology I am using completely. Just go through this terminology because you can understand this terminology. Then only you can easily understand the next steps. Okay, now I place this is the TXC, that is a transmitter coil which is connected to the high frequency converter and DC source, and DC source is again converting to the grid. Now I skip the one step here and directly I place the DC converter, and it is a high frequency converter. I already told high frequency is needed to the transmitter coil to get the more flux linkages to receiver. Now the second one is the INC, intermediate coil, and this is the receiver coil which is connected to the AC-DC converter and DC-DC converter. It is a converter and converter requirement and the battery ratings. Okay. Now here I am three distances I am placing. One is from the ground clearance to the receiver coil. It is the total distance between the two coils, and there will be intermediate coil and transmitter coil. The distances are defined as T1 and T2. Now this will make the main role of the charging system, because the two coil system there will be no INC. INC is not available. INC is not available means what happens? The receiver coil will be very close to the TXC. Then only the efficiency of the total charging system is going to be. If RXC is very large, the distance T is very large. Suppose it is a 15 centimeters between the TXC and RXC, and automatically the flux linkages is going to be more. That means the losses in the fringing losses is going to be the more. And what happened? The system efficiency, the charging system efficiency is going to be less. To avoid that for a long distances, the charging is going to be effective by using this intermediate coil. Now this is connected like a pantograph type. Now it is like a pantograph means it is expandable one. Now it comes close to the TXC, the efficiency levels will be different. If it is near to the RXC, the efficiency levels will be different, and the charging time, everything is going to be decided by the I. That is the main purpose of this intermediate. And I think this one plays major role in the next slides, and the same notations I will use for the different explanations also. Now here I will just comparing the block diagrams of the two coil and three coil system, like just it is a magnetic and electric circuit theory you can apply, and you can draw the equivalent circuits of the two coil and three coil systems. And now here you can see that there is a inverter will be there. The purpose of this high frequency inverter is to get the high frequency, and again I am compensating the inductance of the coil through the capacitor to get the resonance conditions, and also to get the more enhanced efficiency to the coil.
మీకు అదంతా అనవసరం గమ్ అడిగినావు గమ్
And come to this three coil system, there will be three coils will be there. Then definitely the three different mutual inductances is going to be happens here. Now I define that one. It is a M, whatever the defined it is from this coil. These two are receiver and the transmitter coil is M, and there will be M1, 2 and M1. This here, this one will be different colors. The mutual inductance is also different inductances. As per this mutual inductance, we have to draw the equivalent circuits and inductances, everything in the equivalent circuit of the two coil and three coil systems. Now, why you can go for this type of analysis is you have to model the system. You have to model the system, and after modeling, you have to check the performance of two coil system and three coil system. Which one is more efficient for the different mutual inductance? Again, I'm telling here the mutual inductance also depends upon the distance. Distance is directly proportional to the mutual inductance. Now we can solve by using the circuit theory. We can find the of the system or the two coil system, and this is the input resistance at 70 millimeter. That means 7 centimeters and 100 centimeters. Sorry, 10 centimeters and 15 centimeters. And these are the efficiencies of the different distances. Now you can see here 7 centimeters the efficiency versus the load is the efficiency is more. It is around 80%. Now what happens? The distance increases between the coils. That is also the efficiency is also this you have to observe from this. Similarly, for the two coil system, you have to develop the efficiency and output analysis versus load. Now you can see here there will be some difference between the two coil system and three coil system. Now here also the efficiency at 7 centimeters is going to be at 10 centimeters loads, the efficiency is going to be the more compared to the 7 centimeters. Now, there is some particular difference is there for the three coil system and two coil system because of the distances between the coil systems. That is the key point here. Now, the efficiency at larger distances is going to be the more at high. The battery resistance is also there. That point you have to checking the simulations from the two coil system and three coil system for the same distance. Now here I check the receiver at 20 centimeters. This one it is checking up to 15 centimeters because the variation here it is only the intermediate, but receiver coil is fixed at the 20 centimeters. Is it understandable, all of you? Hello. Purna sir?
Sir, yes, sir.
Yeah. Right.
Sir.
Yes. Now, the next thing is you have to model the mutual inductance of this coil by using magnetic field theory. And these are the different parameters we have to consider while considering the mutual inductance design. mutual inductance design. Now this is the output outer radius of the primary coil and outer radius of the secondary coil. Now these are the track with number of turns. Everything you have to take into the consideration. And by using this equation, in modeling mutual inductance coils. Now this is tested in FEM software. Now this is the exact locations and magnetic fields which is going to be happens in Tesla flux density is tested. Here you can check the 3-coil system and the 2-coil system. Now you see here the magnetic flux is going to be more at this points because it is at 6.9 and it is at 5.33. And you can conclude from this one, the system has having the more flux densities and more flux linkages compared to the 2-coil. This is the mutual inductance analysis through the simulation of the car. Now this is the distance, this axis, and this one is the 3-coil system, and this one is the M is the 2-coil system. The 2-coil system means is a M means the mutual inductance between the receiver and transmitter coil, and M0 is transmitter and intermediate coil, and M1 is the intermediate coil, receiver coil, and various distances. The mutual inductance is studied with the help of this. Okay. Now, for this, we propose one algorithm. For this algorithm, we need the different distances of the intermediate coil is going to be computed with help of this input parameter, that is the given system voltage, what is the resonance frequency, and what is the power transfer distance. These all things are the inputs, and we are computed the number of turns is varying in the intermediate coil because it is very important. It is the circulating current is going to be slow because the intermediate coil is going to be closer, and then only the flux linkages is going to be happening. And to reduce the losses in the intermediate coil also, you can check the number of turns is varied some minimum value to the maximum value. That is the max and minimum values is going to be happen between the transmitter and coil with help of this. And this is the check between the number of turns, how it is efficiently it is going to be happening for the intermediate coil. Now the number of turns is varied between the 18 to 22, 18 to 22, and for the different distances, these are the zoom places, whatever I you check this. The efficiency is also going to be varied definitely by varying the number of turns. That things we study in the algorithm. Now see hardware setup, how it is going to be done in the laboratories, and this is the arrangements of the complete structure of the system with a simulator. You are using this simulator programmable one, and we have to see here direct TC supply are taken, and inverter, frequency inverter, and there will be a capacitance, compensating capacitance to compensate the inductance of the current, both the primary, secondary, and intermediate current also. And this is the 6-bit H rectifier, and it is given to the load, and you have to check these are the specifications of the exponent. You are using and turns, what is the unit here, stands, self-inductance, capacitance, coil resistance, wire diameter, inner radius, outer radius, everything, whatever I explained. And also you are using more magnets to enhance more flux. This is the complete hardware setup for the 3-coil system and also 2-coil system. By removing this, you can compare the both. This one is the arrangement of the 2-coil and 3-coil system and gate pulses for the inverter and output voltage of the inverter, which is 60 volts. They tested here at 100 kilo, 99. And whatever I simulated, the same thing performed in the hardware system also, and really matches the simulations and hardware. So you see here the different reason one, there will be efficiency is more for the 7 centimeters, and reason 2 it is 100 centimeters, and at reason 3 at 12 centimeters the efficiency, and similarly the input resistance is also going to be. So resistor input and intermediate coil current also we have to take for the different load settings. PNC is the intermediate current and the input current we also have to check for the same distance to get the efficiency calculations, and also we have to properly check out of 200 meters. This analysis is essential. Now, similarly, you can check the overview of this one. What is the overview of the complete study of the experiment? You have to note it down, and you can check as per which efficiency it is going to be here. Now, it is more at 100. Now, we are studying the complete system at 20 centimeters. Now, you conclude that 10 centimeters it is going to be more efficiency compared to the 7 centimeters INC and 12 centimeters INC. Now this is the conclusion of this experiment study, and it is at 69% of the. And but you see here the power output is going to be more at having more distances, 12 centimeters. That is one of the observation you have to keep in mind, and you can see at application level, and you have to choose the distance as per that requirement and power rating. That is also one of the important parameters. Now see here the comparison, as I told in simulations. I told for 2-coil system there is a 7 centimeter efficiency because the distance is more. What happened? The distance is going to be increasing the efficiency. 3-coil system, it is not like that. It is a 5 centimeter at low resistance is the efficiency is going to be increasing. The efficiency is shifting towards the right. You have to and powers also you have to study. There will be a more power in the 2-coil system compared to the 3-coil system because of intermediate coil. Efficiency and power rating is going to be, power losses is going to be more. This is the summary of this comparison at T equal to 150. And these are the input versus efficiency versus load for the different applied voltages we have to study. And one more thing here, there is a misalignment will be there. Now this is the perfect alignment, first case. Second case, sometimes the parking is not exact to the receiver. Sometimes some misalignment will be there will be a up and down to the down flow. You can regarding to tire issues like that. Due to that also there will be a charging issues. That also you have to study the charging. That is the misalignment study of this. Now compared to that, there will be a misalignment study, and we have to again performing the efficiency and load carry. It is the other study which is a intermediate coil. Sometimes it is going to be misaligned. That comes. Now these are the different losses is going to be happening in the inverter losses and coil losses and diode losses. Is going to affect loss. As per that, we have to choose the reduction methods. And this is the different currents we have to capture at the input and output side. These studies is going to be important for the selection of the power converter devices, diodes, or this currents voltages decides the ratings of the diodes and voltages. This is the conclusion of this three-coil and two-coil system. So, second study is design and implementation of the dual converter. Now you can see that wireless power transfer system is integrated to PV. Now, overview, and these are some objectives. Why you are going to PV integrated to wireless power transfer system is going to reduce the demand from the electricity. Yes, first one is the reduce the yes, you have to reduce the cost electric bill by using this type of integration. And this all things is going to be studied by using the small signal model analysis, and we have to define the transfer functions and PA controller design everything. And once it is going to be done, we have to check with the controller, they have to dump it, and we have to run the system, and you have to check the inputs and outputs, everything. Now, this all things is the objectives of this analysis of the DC. Now, you know, these are the some of the introduction already I explained in the previous. Now, these are the different charging systems available here. Grid-based charging. Solar, you are wireless stationary wireless charging. Now, you are going to combine this second and third. The main node now. Yes. Now we have to see this block diagram, which is PV system, which is available at top of the vehicle, and this is bottom receiver coil will be there and transmitter coil, my power converter. But this PV system is at top of the vehicle, that is roof of the vehicle, and this one, the same diagram is going to be equivalent of the circuit in term of circuit. Now it is a basic boost converter. It is a boost converter which is connected to two sources. Now this the importance is you have to different topologies is coming with help of this circuit. We want to boost converter switching configuration is going to be like this: the first mode of operation and second mode of operation, third mode and fourth mode. Now see one by one. First mode it is the circuit diagram, and first mode there will be switch SPV. Sorry, here it is the first mode. Actually, the first mode it is a SPV and SWPT and S boost is on. Now there is a this switch is open. This switch is open. Now SPV and S boost is on, and this diode is on. Like that. And second mode, both three switches is on. Three switches is on, and diode is on. Similar to this normal boost converter, single input boost converter only the operation. Right. Whenever the S boost is off, then this energy which is stored in inductor is going to be transferred to the diode to the node. That is the basic operation of the boost converter. But here I am operating the two sources with help of the two diodes, inductor and capacitor. Now we have to construct the small signal model. We have to apply the KVL during the state space analysis to make it inductor current and capacitor voltages key role in the small signal analysis. That is one of the things here. And in the third mode, it is first mode, first ST is only one source is operated. In second mode, both sources are operated. And the third mode, wireless charging is only operated. That is the thing. And the fourth mode of operation, S boost is off and it is free will through the sources. Through the sources, what happens that energy is going to be fed back to the sources. Now, this is the negative portion. V naught is greater than, or V naught is less than the VW critical VPV. V naught happens automatically in the negative energy. VPV, second mode it is VW critical VPV and VW is one source, two sources, one source. We have no sources. Sorry, two sources operating depends on the load. And average modeling we have done with help of these four modes, whatever I explained in the previous slides. And we have to construct the functions, and with help of the transfer functions, you can make the find the average voltage and average current and capacitor, inductor, and everything by using these equations and analysis whatever done in the previous slides. And you have to find input voltage and output voltage and everything. And the same converter, wait, I will next I will come to here after next modes of operations. That is the same converter we can operate in buck mode, and boost mode, buck boost mode. Previous is I explained here. This is the boost mode of operation. Now the same pattern, the same converter we can operate in a buck converter. Buck converter means the thing is only the firing sequence is going to be changed. Remaining everything is. Now see the first mode of operation. The switch, whatever I told in the previous boost mode, this switch is on. Which is on for the first three modes. The fourth mode only it is on. But in the buck mode, this is completely not available. No use. No use. Because you are not giving the pulse to the S buck. That is S boost only. Here, call it as S buck. You are not giving pulse. But this is also the same whatever I explained in the previous converter. The thing is, first mode, first source is operated through the load. Second mode, second source is operated. Third mode, two sources are operated. Fourth mode, two switches, all the switches is on. And energy is freewheeling to the batteries. This is similar to the basic buck converter process. Here, the thing is buck operation is similar to that. Now, this there is no first mode, second mode, third mode, and fourth mode. There is no S buck. One switch is absent completely. No operation. And these are the transfer functions for designing the PA controller. And you can have to construct the transfer functions by using the small signal model. And the next mode is the dual input buck boost mode. Buck boost mode, you can see here, first three modes is same as the boost converter. First three modes is same as the boost converter. And fourth mode is same as the fourth mode of the buck converter. Now this is similar to whatever the operation of the single input converters only. The same idea have to be taken and this is implemented. The only thing is the variation of the pitching parameters. Remaining things is same. And you have to construct the transfer functions. You see here, now to transport functions, and you have to construct the step response for the three converters, and you have to check it how it is when the settling time is going to be happening, and you have to construct the body plots for stability conditions and focus point given that anything is going to become uncontrollable. You can adjust the values and you can make the gain values and the stability, and this study is going to be simulated for three converters. The same converter for three modes of operations, that is buck and wait and load. And you have to design the three controllers for the each PA controller 1, PA controller 2, and PA controller 2, because you are adding to the head. You have to construct with help of the switches and comparators, and you have to use some logics to get
Okay.
the SPDI, SWPT, or
Morning, okay. Good evening.
get the required pulses
ఇంట్లో ఉన్నాను, మీటింగ్ ఉంది, ఆన్లైన్ మీటింగ్.
published and so as I explained, there is only two switches will be there for the converter, and similar delays everything which you have to add in for the timer in circuits, which is happening to get the sequence of operation to get the of operation, boost operation, and log boost operations. And details of gain margin and base margin of the controller and gain regulated to study of the stability of the system. And we see the simulation details. For this, the load you are using the lead acid battery and 120. And these are the study of load voltage, yes, charging voltage at 120 volts, and battery terminal voltage. Okay. There is a two sources. One is the solar and sometimes I vary one and sometimes I take it. Disturbances and check controller is going to maintain in the short time to get into the steady state. And these are the switching pulses of inductor of this theory. These are two switching test and inductor mapping. Similarly, buck boost is a booster as well as the buck booster. There will be new negative is less for the same variance. This is the buck converter waveforms with solar to voltage and load voltage and the two inputs and see here I check this for a SOC from 55% to 300 volts from 55 to 55.5 SOC. That means 0.5
Virat? Virat, क्या पड़ी ना होगा क्या पुल देना
to get SOC at 55 stops now. 300 seconds. 300 seconds it takes to reach this 150 volts. Okay. And this is the complete hardware setup for the battery. And this has a battery batteries in series to get the required 130 volts to be converter, which is connected in case of the RO. You tested for some resistors and sometime you connect to the battery, not for a long time. Safety considerations. Okay, these are the specifications we are using for the ledge wire and solar PV panel and specifications of dual input boost converter and battery parameters taken for this. These are the different waveforms captured gate pulses and receiver voltage and receiver current. That means after the inverter voltage, you need resonance condition. Now, because of some there is a disturbance, the current and voltage is not complete resonant. There will be a small lag will be there. Because it is not very typical to get both things is going to get resonance. This is transmitted voltage and current. Now this also need to be make output to voltage and current. This is output circuit. We are getting 62 volts and complete boost converter output state. Now these are the inductor currents for the boost and boost converter. Whatever the simulations we studied, the same things we studied here. We see these voltages of boost or fix values and it is going to be 50. And these are the pulses of the different. And we are checking load is going to be changing, disturbances, how this controller is going to be behaving. This also tested for the test reasons. PR1, PR2, PR3, PR4. PR1 will make the load is constant. And you observe that BPV and BWPP, what is this difference? BWPP is increasing. What happens? You are remaining. And the second, you are test 2 reason you are increasing the WPT. What happens? Now BPV is increasing. First, BPV is decreasing from 60 volts to some voltage, and you observe that increasing the VW. And second, increasing the WPT, there is no disturbance because it's isolation. Remaining all are not disturbing. And load disturbing, what happens now? This is disturbing. And the load current is also decreasing. And we completely off, also is off for the remaining. Now, with all these upload it captured in this waveforms. Okay. What happens suddenly VPV on in the test 5 again there is a decrease. Power balance again will be decreased. So next step is going to be what happens if completely off. Definitely one source is going to give the complete power to the next what happens. WPP source is going to increase. This is one of the studies for the new study is going to happen for the this is the boost mode and this is the not boost mode. Okay, now the all things readings everything is going to be taken from the test bench and the next thing is how to calculate the power losses each and every device and we are using the IGBTs and everything conduction loss, IGBT conduction loss and if all this is going to be studied depends on the data sheets that we are using this in our database and you have to note down this all the parameters. Once you have to note the standard values and you can make the analysis of the losses of the different connections. Why I particularly going through the load conditions because the battery resistance is not going to be the constant all the time of the charge. Because this is very important to have how to take care while designing the battery charge. So these are the results, whatever the observed from the hardware results taken in, and you can construct everything and see the Okay, you see the disturbance effect of inductor voltage and current also here, and the battery also is tested for some charging profile through the LS. This is a complete now conclusion here. I have to make some not this is completely developed now because the scientifically algorithms is we have to check the process is going through the PI that defined correctly for the resources. Each case is developed for the different modes of operations on construct perfect and the simulation of hardware validated for this complete setup with converter. Some references is about the session who queries is
Sir, in 56 number slide, you have used a voltage mode controller or any other type of controller you have used here?
56.
56.
Yes, this is a voltage mode control only. Now here you are see here it is a V naught which is taken from the output of the converter and it is the V reference and you are constructing this is a voltage control.
Then, sir, any ramp signal is needed for comparison for the switching purpose.
No, I am not using here actually. I am using here it is a shortcut carrier.
Sort of. Sir, for the design you have used which software?
This pardon?
Which software you have used, sir, for designing?
Simulations only, not like
MATLAB. For the small signal analysis, you have done mathematical modeling or component modeling, sir.
it is a mathematical modeling only through the
Mathematics.
equations.
First, you linearize all the system using transfer function, and
And
for
how to add some disturbance perturbations to this linearization
uh,
and construct the small signal modelings.
for stability analysis, you have shown Bode plot. For that purpose, you have to use a small. You have to use transfer function. But for other pulses, you have shown in your slide is. Though for those output, you require component modeling, where you have shown pulses and
Entire study is whatever I studied stability and everything is the simulation only.
all
Nothing I
all
read.
are
Yeah.
mathematical modeling.
Yes.
Okay, sir. Thank you, sir.
And whatever I realize the KP and K value, that things I will take and make it in the hardware.
Okay, sir. Thank you, sir.
You need any more research topics, you go through it and I will share my mail ID to
Mm.
Purnachandra, sir. You can go through it. Okay, you just,
Okay, sir. Please, sir, share your email ID.
yeah, sure. The chart I will share it.
Okay, sir.
got it?
Yes, sir. Thank you, sir.
Anything, any Purna sir?
Sir, any questions from audience?
Yeah, thank you to all.
Any questions from audience? Any questions? Sir Kamal sir,
Yeah,
1 minute. Dear participants, on behalf of Sri Venkateshwara College of Engineering and Technology, I would like to express our sincere gratitude to Dr. Kamalapati for his insightful session on wireless charging technologies for EV. Dr. Kamalapati, your expertise in this emerging field has significantly expanded our understanding of wireless charging systems for electric vehicles. Your clear explanations and engaging presentation have made complex concepts easy to grasp. Thank you for taking the time to share your knowledge and valuable insights with us. We look forward to more such sessions in the future. Once again, thank you. Sir, thank you, sir.
thank you, Purna Chandra. Thank you. Thank you very much. Thank you all.
Thank you, sir.
Yeah, thank you.